Hello, my name's Jeff Messier. I'm a professor in electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is Module 8 in my Computer Networks lecture series, where we look at evaluating the performance of error detection schemes. So at this point in the course, we've looked at 3 error detection schemes. We've looked at the single parity bit, the internet checksum, and the cyclical redundancy check. And, we've kind of made general observations that the parity bit is, not so good and the CRC is really good. But we haven't really put any numbers behind those observations. And so that's what I'm going to do in this module. And basically, we've learned that each error detection scheme, all error detection schemes are vulnerable to certain error patterns. There are some error patterns that they're just simply not going to spot. And sort of fundamental to evaluating the performance of error detection schemes is determining the probability that those error patterns may occur in a received frame. And so that's where we're going to start. This is kind of like the fundamental bit of foundational knowledge that we need. And then we're going to extend that knowledge to look at both the performance of the single parity bit and the CRC. Okay, so let's start by introducing a bit of notation. So the probability of a bit error occurring because of noise or interference at the physical layer, we're going to denote just by little p. In past modules, we've used p sub e, but I'm just going to use a lowercase p here just to keep the notation a little bit simpler. And our objective is to come up with probability expressions for different error patterns occurring. And so let's start this out by considering a specific error pattern. So let's consider a 4-bit packet and determine the probability that the second and third bits are bad. So 4-bit packet. So the probability that second bit and third bit is bad is equal to the probability that the first is good and the probability that the second is bad and the third is bad and the fourth is good. So if we assume that bit errors are independent at the physical layer, which is a reasonable assumption in most systems, the probability of error is going to be independent in each of the bits. And so when we look at the intersection of these probabilities, we can write them as the product of the individual probabilities. So this is equal to the probability that the first bit is good multiplied by the probability that the second is bad, and so on. Which is just equal to, so if the probability of a bit being bad is p, the probability that it's good is 1 minus p. So this is 1 minus p times p for the second bit times p for the third bit times 1 minus p for the fourth. And we can consolidate this and write it as p squared times 1 minus p squared. And so that's the probability of a very specific bit pattern occurring. But if you'll remember when we were, in particular, when we were looking at the parity check bit, we would say that any even number of errors would slip past the error detection scheme. So any 2-bit error, any 4-bit error, any 6-bit error, and so on. And so we want to, in many cases, determine the probability of any 2-bit error pattern. And there are a whole bunch of ways of having 2 bits bad in one packet. The first 2 bits could be bad and the rest could be good. The first and last bit could be bad, with the middle ones being good, and so on. So the way that we calculate this is by using the combination formula. So you can imagine us basically choosing a certain number of bits from the packet that would be in error. And we can use the combination formula because it doesn't matter, the order that we select the bits. So for example, if the first 2 bits are bad, it doesn't matter if I choose the first one as being bad and then the second one, or the second one and then the first one. So in general, the number of ways our bits can be bad in an n-bit frame is equal to n choose r. And that means that the probability of r bits being bad in an n-bit frame is equal to n choose r times the probability of r bits being bad and the remaining n minus r bits being good. And this is a general expression that we're going to use in a number of places in the discussion to follow. Okay, so let's do an example for our parity check, our parity bit error checking or detection scheme. So in our previous module, we considered an 8-bit very simple frame with a 7-bit payload and a single parity bit checksum. And we know that this scheme fails if it experiences an even number of errors. And so in our case, that's 2, 4, 6, or 8 bits. And so the probability of a miss, the probability of missing an error, is equal to the probability of a 2-bit error. So there are 8 choose 2 different error or different ways we can have 2 out of 8 bits being bad. And if you want to check this, you can sort of go through it exhaustively to satisfy yourself. So it would be the first 2 bits, then the first and the third, the first and the fourth, and so on. The probability of all of these 2-bit errors is the same. It's the probability of 2 bits being bad and the remaining 6 bits being good. The probability of a 4-bit error is 8 choose 4, p to the 4, 1 minus p to the 4. 6-bit error, and there's only one possible 8-bit error pattern, and that's all of them being bad. And so if we consider a physical layer error rate of 10 to the minus 3, which is not great. Most will do better than that, but this is, maybe kind of a reasonable raw physical layer error rate without error correction codes. And if we plug this value for p into this formula, we get a probability of missing an error pattern equal to 2.8 times 10 to the minus 5. Now, I want to dwell on this number for just a minute because this seems super, super small. So for example, if you were a student and you only got and your rate of getting questions wrong on assignment or on exams was 2.8 times 10 to the minus 5, you would be an amazing student. You would have a 4.0 GPA, hardly ever made a mistake, all kinds of awards. So the question is whether or not this is low enough for the internet. And as it turns out, this is a terrible result for an error detection scheme. And so this means we have one missed error packet per approximately 36,000 received bytes. And that's basically just 1 over p miss, adjusted for byte size. And so that means roughly every 36,000 bytes we receive, we miss a bad one. And so if you missed an exam question every 36,000 exam questions, no problem, right? You'd be super happy with that. But on the internet, because we send so many bytes, this is terrible performance. So most of the file transfers that we perform over the internet are larger than 36,000 bytes. The average web page size is into the megabytes. Certainly if we're transferring an app, it's way bigger than 36 kilobytes. And so we would be sending bad bytes up the protocol stack without noticing them much, much too frequently. And so this is one example, and this theme is going to be coming up over and over again, where we have to have super good reliability for internet communications, because the number of bytes, just the vast quantity of information we send over the internet, is so huge. So the parity bit isn't good enough for internet level communications. How about the CRC? Well, in order to evaluate CRC error detection performance, we need to say a few things about the types of error patterns that will be missed by a CRC checksum. And we've seen that we can think of bit errors as being equivalent to an error polynomial that gets added to the transmitted frame. And we saw in the examples that we did last module that basically a CRC checksum will miss any error patterns that are evenly divisible by the generator polynomial. And we need to then just try to figure out or approximate the number of error patterns that we can expect that will be evenly divisible by our generator. And in order to do this, we need to have a notion of the length of an error pattern. And the length of an error pattern is basically the number of bits in the error pattern starting at the first one and leading up to the last one. So for example, if we have the following error pattern, this is our first one, this is our last one. And so we would say that the length, whoops, that didn't work very well. Let me have a slightly smaller pen. But the length of this error pattern is 6, right? 1, 2, 3, 4, 5, 6. If there are leading or trailing zeros, we don't include those. And so if k is the degree of our generator polynomial, then all error patterns of length less than or equal to k will be detected. And so if we think about our previous module, we had a generator, whoops, yikes. We had a generator polynomial of 1, 0, 0, 1, 0, 1. And we did our long division until we got a bit sequence that was shorter then the generator polynomial, and then we had to stop. And so no error pattern that is 5 bits or less can be evenly divided by the generator polynomial. And so the generator polynomial in this example is x to the 5 plus x squared plus 1. And so the degree is equal to 5. And so any error pattern less than or equal to of length less than or equal to 5 cannot be evenly divided by the generator. So this should be less than or equal to, that's not very easy to see, less than or equal to k will be detected. So does that mean that all error patterns of length 6 or more slip through? The answer is definitely no. So the vast majority of these longer error patterns are also not evenly divisible by our generator polynomial. In fact, the fraction of error patterns longer than longer than k that are missed is approximately 1 over 2 to the k. So in our case, 1 over 2 to the 5 is the fraction of errors that that are missed. And so I'm going to then take this information and incorporate it into an example, and we'll figure out the probability of missing some bad bytes when we use a CRC. Okay, so let's do a CRC performance example. Now, to be a fair comparison with the parity check code, let's assume an overhead rate. Oops. An overhead rate of 1 over 8. So that means 1 CRC checksum bit for every data bit. For this example, let's assume a CRC length of 16 bits. And that means that we have a frame length of 128 bits. Now, we've seen in the previous slide that the probability of a CRC miss is equal to 1 over 2 to the k, where in this case, k is equal to 16, times the probability of an error pattern of length 16 plus the probability of an error pattern of length 17, and so on. And so that's the general form of the equation. Now, what I want to do is talk a little bit more in detail about how to figure out the probability of having an error pattern of a certain length. Because an error pattern, so let's say, for example, we had an error pattern of length 3. That's not the same thing as having 3 bad bits, right? So just to clarify that, and rather than using 16 and 128, which is, maybe gets a little bit long and a little hard to draw, let's consider an example where, we have a frame length of, let's say, 6 bits. And so the probability of having an error pattern of length, let's say, 3, if we were to draw this out, we have 6 positions in our frame, right? So 1, 2, 3, 4, 5, 6. Now, to have an error pattern of length 3, that means that we have to have, one bad bit, let's say here, for example, one bad bit here. So our error length, or the length of our pattern is 3, right? Because the length of an error pattern is the number of bits starting on the first bad bit and ending on the last bad bit. And that means that all the bits outside our error pattern are good. What about the bit inside our error pattern? Well, we actually don't care about that one. So this bit could be bad or it could be good, but it doesn't really matter. The length of the error pattern is defined by, the first and the last bits that are bad, and it doesn't really matter what's going on in the middle. Okay, so just cleaning up our screen a little bit here. This is a picture of the error pattern of length 3. Now, let's write the probability expression for it. So we said that, the first and last bit in the error patterns have to be bad, right? So so the first bit in the error pattern has to be bad. That occurs with probability little p, if p is the probability of bit error. Then the middle bit we really don't care about. So it can be good or bad, and the probability of being good or bad is just equal to 1. So this is multiplied by 1. We then have our last bit being bad, so that occurs with the probability p. And then we have to have all our other bits good, right? So that's 1 minus p cubed. Right, so basically the general form of our probability expression is, p for the first bit, p for the second bit, 1 raised to the exponent of the number of bits inside our error pattern. In this case, it's just equal to 1. And then 1 minus p raised to the exponent of however many bits we have outside of our error pattern. And so if... again, kind of cleaning this up a little bit here. What's the best way to do this? Let's try this. Okay, so if this is, I'll move our error pattern over here and our specific expression over here. So let me write a general expression for the probability of having a certain number of bits bad in our frame. So the probability of having an error pattern of length L in n bits is equal to a single p for the first bad bit times 1 raised to the exponent of however many bits we have in the middle of our error pattern, which is equal to L minus 2 times bad bit probability for the last bit in our error pattern multiplied by the probability that all the other bits outside our error pattern are good. So this is n minus L. Now, the only other thing that we have, the only other thing that's missing is we have to recognize that an error pattern of a certain length can occur really anywhere in our frame, not just in one position. So the specific expression I wrote up here was for an error pattern that just happened to start on the second bit. However, in general, I just get rid of this expression here. Remember we had we said that our length was equal to 3, right? Now, it just so happens that we lined up with the second bit, but we could have a error pattern of length 3 that starts on the first bit, the second bit, the third bit, or the fourth bit. And so we just multiply this general expression by the number of possible positions that we have for our error pattern, which is equal to the number of bits in our frame minus the length of our pattern plus 1. Okay, and so this is the general form of having an error pattern of a certain length in a certain number of bits. And what I'm going to do, I'm not going to like do all this math. I just wrote a Python script for this, but I'm used this expression up here in our original equation for the probability of a CRC miss. And so I calculated the probability for an error pattern of length 16, 17, 18, 19, 20, all the way up to 128, added them all up. And then when I did that, again, I'll just try to make some room here. Oops. So the probability of a CRC miss, I got to be equal to 8.97 times 10 to the minus 8. And so the average number of megabytes we have, between bad bytes or between bytes that are missed is equal to 170.1 megabytes. So basically we can transmit 170.1 megabytes before we have a bad byte slip through due to a CRC miss. So a lot better than the parity bit for sure. 170 megabytes, that's not huge, right? Like you can't even download a movie for that much storage. But remember, the probability of bit error that we've assumed is 10 to the minus 3. And this is super, super high. So there's really no links on the internet that would have a raw bit error rate probability of 0.001. And so because of that, the performance isn't great, but we can still see, relative to a parity, just the simple parity check bit, the CRC performs a lot better, which is basically why it's the industry standard.